In Chapter 8, we learn about magnetic forces on a wire, torque on a wire, an application of torque on a wire, which we'll study and we'll need to use for our bike project about electric motors, creating currents in moving loops, and eddy currents in moving conductors. So force on a wire, just like we were learning about forces on a moving charges. If we think about a wire, right, this wire has positive charge. If I think about current, the model for current is that I have these positive charges, and let's say the current is moving to the right. So I is to the right. And then I can think about this current as positive moving charges and think about my right-hand rule. So if my fingers point in the direction of the positive moving charge, and let's say that I have the B field, let's say we have it coming out of the page here. So these are little the tips of the arrows here coming out of the page. Then I know my force is going to be down. That's going to be the magnetic force. And so now instead of thinking about moving charges, I can just think about current. So I put my fingers in the direction the current is flowing. So in this case, the current is flowing to the right. The B field is out of the page, so my force is down. If I had an example where my current is flowing to the right and my B field is into the page, then I point my fingers in the direction of the current. So I point my fingers this way. I bend into the page, and my force is going to be up. So it's the same right-hand rule that we would use for moving charges in a magnetic field. Note too that here, notice the equation B bar over C. We have, in this case, in B bar has units of newtons per coulomb, whereas here I just have Li crossed with B, and the magnetic field is in Gauss. My L here is the length of the wire. So some of the problems you'll see have the length of the wire. They'll say find the force per unit length. And so what that means is I don't have to worry about the length. I'll assume this is 1 meter, and I'll just have 1 over C I cross B bar. We're going to do hopefully a demo in class where we have a wire, and the wire has a pretty current going through it, and the current's big enough that when we put it into a magnetic field here in a horseshoe magnet, we should see a force acting on the wire. So if my current is traveling this way, so say into the page, and I have to bend my fingers, I'm going to bend them to the right, and so my thumb represents the force, and so the force would be down. So this horseshoe magnet should force my wire down as long as there's current flowing in that wire. And so again, we use like I said, we use the right-hand rule. So we have F. Let's just go back. F is equal to L over C, I cross with B. So or L times I, and then this B is in Gauss, and then so the cross I use sine theta. Again, the biggest force I will experience is when my current is perpendicular to my B field. And we've already gone through this direction. We use the right-hand rule. Fingers point in the direction of I bend my fingers in the direction of B, and my thumb represents the force. So we'll do this problem in class. What is the magnitude of the force per meter of length? So you see that force per meter of length. That means that I'm going to assume it's that my length is 1 meter, and so I'll simplify the problem just a little bit. And now, just as a magnetic dipole experiences a torque, so does a magnet, and thus so does a wire experience a torque. So if there is a magnetic field and a wire, then the magnetic field will cause the wire, the current carrying wire, to rotate so that it's aligned with the magnetic field. And so we can represent the torque. It's given by this equation here, this torque, and that's mu. This is mu crossed with B bar over C, and where mu is N, the number of turns in my wire. So imagine I have a loop of wire, and this would be the number of turns. So imagine I had a wire and I was wrapping it around, say, a spool of thread. Then N would represent how many times I wrap it around that spool of thread. area would be the area of the face of that spool thread, so that circle, right, would be like pi r squared. And then I would be the current that's going through that, that wire. And my direction here my direction is going to be represented by this south to north orientation of this loop's equivalent magnet. And we'll talk about that in just a minute. But this represents the direction for that loop of wire. And mu is called the loop's magnetic moment. So this is how we can calculate the actual value of the torque, right? So if I'm thinking about torque, then the more my the faster my wire rotates represents how the value, the strength of the torque. Okay, so this is what we're talking about when we're talking about this representing our loop as a magnet. So if I go through this loop right here, and I think about what forces are acting on each of these segments. Let's start with this top segment. If my current is flowing in this part right here, if I look down here, they show me an arrow. So on the bottom it's flowing to the right. Here it's going to be flowing up. Here it's going to be flowing to the left. And here it's going to be flowing down. So right on this part right here, if I point my fingers in the direction that the current is flowing, so to the left, and I bend my fingers in the direction of B, then my thumb is going to be pointing up. So on this part of the loop, I have an upward force. And now if I go down to the bottom, and I point my fingers in the direction of I, and I bend in the direction of B, then my thumb is going to represent a downward force. So and now let's talk about the sides. So if I point my fingers down and I bend in the direction, I'm going to have a force that's out like this. So this would be one of my forces. And then if I do the same over here, I have another force that's going to go this way. And so the interesting thing about that is those two forces, this one and this one, they cancel each other out. They're both pointing in opposite directions. These forces, though, actually don't. And that's because my loop is at an angle. So since my loop is at an angle, if this were perpendicular, if this loop was perpendicular to the magnetic field, then they would cancel. But since they're not, I'm going to have a force up on this side of the loop and a force down on this side of the loop, and that's going to cause my loop to rotate. Right? So imagine if I took this loop and I pulled on the top like that and I pulled on the bottom, it's going to cause my loop to become perpendicular to the B field. So that would be the torque. Just like it shows here on this the axis, it's going to cause it to rotate from looking from the left counterclockwise. And then we were talking about one model that we can use for a loop is that we can assume we can think about the loop as its own magnet. And so one way to do that is if I take my fingers and I point my fingers, or I align my fingers like in a loop around this wire. So I curl my fingers. I curl my fingers this way. Then my thumb is going to represent the north face of a magnet. So I'm curling my fingers like this, and my thumb represents this north face. So that's a model that we can use that makes it easy to figure out how this loop is going to rotate. Instead of going through all of the segments of this loop, I can just imagine it as a magnet and then say, well, my magnet wants to orient to the B field, so I know that this magnet's going to rotate up so that its north face is pointing in the direction of the B field. So again, I know that this is going to rotate counterclockwise.